This is part 2 of our video covering processors and instruction sets. In part 1 we worked through roughly the first 10 slides of the slideshow, and we went over the basic set of instructions that would be needed to implement any quote-unquote full-fledged or full-fledged, let's call it, CPU. So a CPU that can run a program that can do any of the things we would expect a modern computer to be able to do. Quickly reviewing that instruction set, there were move instructions that move data to and from memory locations and registers. There were a handful of instructions to implement the Boolean processing operations and or not XOR. There was an add instruction to do addition, and there may be multiple versions of that if there are multiple data types supported. There was a shift instruction, which can be used to extract individual bit values and test them, or can be used to do multiplication or division. There was a conditional branch and an unconditional branch and a halt instruction. So depending on how we counted that, we wound up with somewhere between a dozen and a dozen and a half instructions, and we discussed the fact that in a very early processor, such as we'd see in a computer of the 40s or 50s, that was all there was, but that was actually enough, because more complicated things like subtraction and multiplication by things other than 2 and square roots and exponentiation can be accomplished by piecing together these primitive building blocks in more complicated ways that can do those more complicated functions. So what we're going to do in part 2 here is we're going to pick up right on that theme, and we're going to go over one very simple example that's in your book and in the slides of how to implement subtraction using nothing more than the instructions in that primitive set. Okay. We're then going to walk forward and cover some related topics, including instruction format and clock rate and things like that. And then we're going to return to and kind of conclude this issue of simple versus complex with a discussion of RISC and CISC processor design paradigms. So we're going to pick up on this theme by working on this example that's in the middle of the slide. We're going to show how to implement subtraction using the primitive building blocks of XOR and add. And the example we're going to show is to subtract the decimal value 3 from the decimal value 10. Now what I've done is I've copied some portions of this example, basically that, into a notepad window here that I'm going to use. So this is the portion that I've copied in from the slide. And I need cover a couple of preliminaries first, and then we'll talk about how we're going to walk through it. The first preliminary is taking you back to elementary school, or perhaps middle school. I'm not sure exactly where this material is covered. But at some point in your academic life, you should have, in a math class somewhere, learned that addition and subtraction are really two sides of the same coin. And that in particular, if I want to subtract one number from another, where both numbers are positive, I can view that not as a subtraction operation, but as an addition operation where the second number is negated. So in this particular example, 7 minus 3 produces the result 4, but I can also use addition, okay, and take 7 and add to it the negative of 3, and that will also generate 4. Okay. So if I have the ability to take this 3 and flip it over to a negative, then I can take the subtraction operation and in essence convert it to an addition operation. And of course I already have addition, or add, as an instruction in the primitive instruction set. So this example takes advantage of this simple correspondence to allow me to do subtraction without actually having a subtraction instruction. Okay, so we're not quote-unquote actually going to subtract. What we're going to do is we're going to add, but we're going to add a negative number to generate the same result. Second thing we have to cover is the issue of how we represent 7 and 3. This goes back to chapter 3 and our discussion of 2's complement. Okay, You'll recall from that, or maybe you don't, but I'll review it quickly here, that in 2's complement we represent a positive number as simply its ordinary binary representation. Okay, and note here I'm working with strings of 8-bit values, and I'm working with 8-bit strings, and I'll come back in a minute to why I'm doing that. Okay, so looking at this bit string, this is the 1's position, this is the 2's position, this is the 4's position, the 8's position, so on and so forth, moving to the left. And the decimal value 7 is 4 plus 2 plus 1. Okay, so the proper representation, assuming I'm working with 8 bits or strings, bit strings of length 8, would be 5 zeros followed by 3 1's, and that represents the decimal value positive 7. So let me go ahead and stick in the plus there just to make it explicit. Okay, what about 3? Well, let's start with the positive version of 3. Well, there's the 1's position, there's the 2's position. 2 plus 1 is 3, so I have 1's in these last 2 positions and zeros in all the leading ones, and that's the positive version of 3. Now, what about the negative numbers? Well, the negative numbers, of course, are a little more complicated. What we have to do to represent a negative number is, or one way to think of it is, we start with the positive representation, which is this, okay? We then flip every bit. So all of these zeros would become 1's, and all of these 1's, or both of these 1's, would become zeros. And then we add 1 to the result. And that gives us the negative representation of the positive equivalent. Okay, and if we look at this sequence of instructions right here, XOR of this first bit string to this second bit string, and then the outer one, which adds the result to 1. That's exactly what's happening here. So, sorry, I'm having trouble highlighting this all correctly. So this sequence right here, okay, is the sequence that converts the positive representation of 3, which is these 2 1 bits right here, into the corresponding 2's complement representation of the negative value that corresponds to that. Okay, so this transformation is something you might imagine would happen quite a bit inside any programs that do computations, because negating a value is something that happens very commonly, okay, in mathematical functions. Okay, and looking at it down here, okay, there is the piece of it I need to work on. Now, before I go any further, let's talk about how I'm going to walk this through. Rather than show you every individual bit manipulation, because that gets a little tedious, we're going to cheat a bit, and we're going to use the Windows calculator. And the Windows calculator, if you open it up and go to the View menu, has a handy little programmer view, which is what I have displayed here. Now, the example as it's printed in the textbook and on the original slide shows 4 or bit strings of length 4. Unfortunately, our Windows calculator, the smallest we can go is a byte, which is 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Of course, we also have words, which are 16, double words, which are 32, and quad words, which are 64. But let's try and keep the number of zeros. We have to shuffle around down to a dull roar, so we'll stick to bytes. Okay. So the first thing I'm going to do here, let me minimize this, and actually I'm going to minimize this as well, okay, is I'm going to convert the values here in this first line of the set of transformations to 8-bit values. Okay, so this value here is the one that represents 3. So instead of just 2 leading zeros, I need 6 leading zeros. 1, 2, 3, 4. Okay, to flip the bits, I'm going to XOR against a string of 1's, so I need 8 1's, not 4. Okay, the value positive 1 is going to be represented with a 1 in the 1's and a whole bunch of zeros in front of it, and I need 4 more of those zeros in front. Okay, this is the representation of the value 7, okay, and it also needs 4 more zeros out front. 1, 2, 3, 4. Okay, so now we have bit strings of length 8, which we can plug in and out of this calculator fairly easily. Okay. All right, so let's start with the first step of converting positive 3 into negative 3. To convert positive 3 into negative 3, we can XOR, exclusive OR, the bit string that represents the positive value against a bit string of 1s. And you once again recall from chapter 3, what XOR says is if I have a 0 and a 1 or a 1 and a 0, then the result is then the result will be a 1. And if I have two zeros or two ones, then the result will be a 0. So this strategy here of XORing a value against a string of 1s is very commonly implemented in low-level programs. And basically what this allows me to do is flip every bit position in what's here to the left. Okay. So let's make a copy of this. So if I take this string, and I'm going to copy it in here. Okay, note it strips off the leading zeros, but I can see them there. And if I XOR that, click XOR, against 1, 2, 3, 4, 5, 6, 7, 8 1s, and hit equals, I wind up with this string, okay, 1, 1, 1, 1, 1, 1, 0, 0, which as you can see is just basically the bitwise opposite of what I started with. Okay, so taking this and copying it onto the next line and replacing this with the value up here, I have 1, 1, 1, 1, 1, 1, 0, 0. Okay, and just to make that obvious, let's see, let's line it up that way. Okay, or I'll see. There, that makes it a little more obvious. Okay, so this, once evaluated by our calculator, produced this value. Okay, so that's half of the processing we need to convert plus 3 into negative 3. Okay, we first flip all the bits, which is what we just did with the XOR. The next thing we have to do is we have to implement this add operation. We're going to add 1 to the whole mess. Okay, so we're going to take that value and we're going to add this value to it. So I've already got the 11111100 displayed in the calculator. I'm going to, and we're working in binary, so I'm going to add to that the value 1, producing this string as a result. Okay. And so let me do another copy operation here. And now what I'm going to do is I'm going to replace all of this with 11111101, and now let's put this there. Okay, so this bit string is the 2's complement representation of negative 3. Okay. Okay, and let's put that up here just for reference. Okay, now that I've negated the 3, what I can do is go ahead and implement this. I'm simply going to use the add instruction to add my bitwise representation of negative 3 to my bitwise or 2's complement or 2's complement representation of negative 7, and what I should generate is a result that can be interpreted as 4. Okay, so here's the representation of 7. Okay, let's take that and copy it. We're going to add 7, and that yields this bit string here. And I'll pre-pad it with the zeros so that it's obvious. 1, 2, 3, 4, 5. Okay, so there's my result. What is this result? Well, 0 in the 1s, 0 in the 2s, 1 in the 4s, zeros everywhere else. So this is the representation of positive 4. Okay. Now, do I expect you to be able to do this on a test? No. Do I expect you to be able to do the, well, I could have given a weekly assignment that would you do something like this, but I didn't. Okay. My point here is not to teach you how to bit fiddle. My point here is to convince you that it is possible to do something do a processing function for which you do not have a specific instruction, in this case subtraction, by combining in the appropriate sequence a sequence of operations that use the primitive instructions you do have, which in this case were XOR and add. Okay. Now, it's a bit of a leap of faith, but if I can do it for subtraction, guess what? I can do it for more complicated things. I can do it for square roots. I can do it for multiplication by things other than 2. I can do it for exponentiation. I can do it for logarithms and sines and cosines and all sorts of weird and wonderful, more complex formulas. Will it only take 3 lines to do it or 4 lines to do it? No. The more complex the function I'm trying to emulate with these primitive building blocks, the longer the sequence of operations it's going to take to do that. And in the case of some fairly complicated math, you wouldn't be surprised if there were hundreds or thousands of these primitive instructions that had to be executed in order to do that more complicated function. But the fact is, it can be done if you simply write the proper program. And if you were a programmer back in, say, 1955, programming, I don't know, finance calculations in an IBM mainframe for, computing interest on a bank account or something like that, that's exactly what you'd be doing. Okay, you'd have a kind of a trick bag of, well, if I want to do, exponentiation, then here's kind of my template, the set of primitive building blocks in the order in which I execute them. And if I want to do a square root, or a cubed root, well, here's another set. And you'd kind of have a library of these things. Of course, remember, this is the days in which computers had pretty limited memory, so library didn't mean, you opened up Windows and grabbed it from a file. Library meant you opened up a file cabinet and pulled out some notes that you'd hand scrawled somewhere, and now you started writing a program that implemented those notes. But the point is, for every more complex process, there is some sequence of these primitive building blocks that will quote unquote do the trick. Okay, so let's come back then to the more general issue of simple versus complex. Okay, so as we've shown, we can do something more complex by combining the primitives in the appropriate format. Okay, what are the cons of doing it, or pros and cons of doing it that way? Okay, what are the pros of having a processor that has only this minimal instruction set? Okay, well, there's 2 pros. Pro number 1 is it's a pretty simple processor. Okay, we don't need 1 billion transistors. We maybe need a couple hundred, or at most a few thousand, depending on how many bits at a time we're going to operate on. So for an 8-bit set of operations as we did here, we can probably get away with 1,000 or 2,000 processors or transistors. And just as an aside, if you go take a quick look towards the back of chapter 4, you will see a figure in there that displays the traces associated with an Intel 4004 processor, and that would be an example of a processor that implements these primitive instructions, actually does a few more, but not a whole lot more, on 8-bit data inputs. Okay, and I think it's got like 2,400 transistors in it or something like that. Okay, so clearly a processor with 2,400 transistors in it is much cheaper to build than one with 2 billion. Okay, the other advantage of this is, and we've hinted at this earlier, but we're going to beat it to death in this chapter. Simple, okay, means smaller. Okay, fewer components, fewer wires, shorter distances between them. Simple and smaller are not only cheap, they're fast. Okay, so while, for example, a current core 2 processor, might top out at a clock rate of about 3 gigahertz, if Intel was to take exactly the same fabrication process and go back and, rebuild the Intel 4004 on its current 22 nanometer processor, it could probably be getting clock rates 10, 20 times that. Okay, now I'm sure there's some other physical limits it would hit, but the point is simpler means faster. Okay. What are the cons of this? Well, so we know the processor's simple, we know it's cheaper to build, we know it's going to run very fast, but there must be a cost. Okay, what's the cost? Well, the cost is in the programs. Okay, To do the more complex things, we need long sequences of instructions. Those long sequences have to be written. Those long sequences have to be debugged and tested. They have to be stored on disk. They have to be loaded into memory. Okay? And although the processor that's running all those hundreds or thousands or millions of instructions is very fast and very simple and very cheap, the program that processor is running is very complex. Building or programming that program is expensive, and it's slow, and it's error prone. Okay. Now, kind of a preview, because I don't want to hit it really right here, but notice the pros here are kind of all on the hardware side. The machines and the cons are mostly on the labor side, because it's people that write programs. Now, of course, if we take people out of the equations and assume programs can write other programs, then it's just hardware against hardware. But if we think of programming as being a labor-intensive process, and if we think of the machine as being a machine, we're really talking about all the pros being on the hardware side and all the cons being on the software or the labor side. Okay, keep that in mind. We'll come back to it later in the chapter. So, of course, as we saw in the Intel manual, we've got a hell of a lot more instructions than that dozen to a dozen and a half in a typical modern processor. Okay, we've typically got hundreds, okay, pushing upwards towards 1,000. Okay, lots and lots and lots of them. Okay, why? Okay. Well, we've already discussed part of this in part 1 when we were discussing the add instruction. Do we have just one add instruction? No, we've got several. Why do we have several kinds of add instructions? Well, one reason we have them is because we've got lots of different data types. Okay? We have, for starters, integer and real. Okay, and remember, integers are represented as 2 complement, and real numbers are represented using IEEE floating point format. Now, the example we just walked through was 2's complement. So this particular sequence of operations worked to do subtraction on 2's complement values. Would the same sequence of operations work if this value here was, instead of 2's complement, IEEE floating point representation? Well, probably not. Okay, we would probably need a very different set of transformations in order to subtract one 32-bit IEEE 754 number from another 32-bit IEEE 754 number. Okay, so integer and real automatically give me 2 versions. Well, but then within integer and real we get into variations. Okay, well, on the integer side we've got signed and unsigned. We also have short and long. Okay, or single or double precision. Remember, there's 3 different IEEE representations. There's a 32-bit, a 64-bit, and an 80-bit. Okay, so when we start accounting for the fact that there's probably 5 or 6 or 7 or 8 different numeric data types in this machine, we're going to wind up needing 5, 6, 7, or 8 duplicate quote-unquote add instructions, and they're duplicates simply in the sense that they do addition, but they're not duplicate in the sense of the underlying processing components, because the underlying processing components differ to account for the different representations. Okay. What else is in that those extra instructions? Well, although we showed we could do subtraction by doing XOR and a few adds, most modern CPUs are actually going to give you a subtract instruction. Okay, why? Well, because subtract something you do a lot. Okay, you're going to do a lot of subtraction in a program, and rather than forcing you to write 3 or 4 different instructions to do it, why not just give you one that's quote-unquote customized to that? And while we're at it, why not give you a direct multiply and a direct divide, and maybe some higher order functions as well? Okay, so in order to make it easier to program, so that we can write a program with fewer instructions in it, we're going to take those primitive building blocks and we're in essence going to pre-combine them into processing circuits or instructions that do these higher order functions. Okay, ditto with the logical functions. Okay, We didn't walk through an example, but you can use XOR followed by a conditional branch basically to implement a simple if test for equality on a particular bit value. But what about when you want to get into more complicated things, greater than or equal to, or less than or equal to? Okay, it makes sense to actually have conditions and conditional branches based on those conditions that implement all of the possible logical variations. If we come back here to the data instructions, that's what all these C moves are about. Okay, so there's a conditional based on equality, there's a conditional based on 0, there's a conditional based on not equal, greater than, less than, so on and so forth. Okay, so that accounts for quite a few of these extra quote-unquote conditional moves. Okay. And the last one, and this is one we'll come back to, because this is, if there's a sticking point here, it's this one. Okay, instructions that combine data movement to and from memory with an actual processing function. Okay, so for example, an add instruction that doesn't assume that its inputs are coming from registers, but assumes they're coming from memory. Okay, so an add instruction where the opcode says add, but the two operands are memory addresses. Okay, so how is that a complex instruction? Well, because the two operands are memory addresses, in essence, what we've done is we've combined add with two moves. Okay, because we know for the ALU to do the add, we actually have to have the data in general purpose registers, because that's where the ALU reads its data from. But if the instruction format says memory address, then in essence what we've done is we've combined a move from memory to register for both of the operands with the actual add instruction. So we're doing three things at once. And of course you can imagine a fourth one where it's, grab this data from this memory address, grab data from this memory address, and when you're done, by the way, store it back to this memory address. So that would be move, add, followed by a move of the result to the memory address. Okay, so for all of these reasons and some more that we haven't discussed, we've glossed over, a modern CPU has hundreds of instructions, not a dozen or a dozen and a half or two. Okay, why? Well, it really boils down to one thing, and this is very basic economic fact. Given modern fabrication capabilities and given modern the way we build programs, it is cheaper to embed the complexity in the silicon that implements the CPU than it is to quote-unquote embed the complexity in the programmers. Okay, silicon is cheap, at least on a per unit basis. Programmers are expensive on a per unit basis, and therefore simple economics says, put the complexity where it costs the least. And where it costs the least is sitting inside a Core 2 or an IBM Power 6 or whatever other CPUs we've got floating around there with 1 billion plus transistors in them and all the wiring necessary to put them together, and the hundreds of 64-bit and 128-bit instructions that implies. Okay, and that makes life easier on the programmers, which is good because programmers are people and we like to make life easier on the people. Well, it's good in that sense, but not, maybe it's bad in another sense. To the extent we make it easier on the programmers, well, now we need fewer of them or we don't have to pay them as much. Okay, moving forward to the next issue, instruction format. And we kind of previewed this with the discussion I just gave you of complex instructions. So different instructions have different formats. Why? Well, really it's due to the number and the type of the operands. Okay, if I assume that the opcode is a fixed width thing, which it always is, okay, but if I have, let's say I have the add instruction, and let's say this is an add instruction that where the operands are all register numbers. So I've got 16 general purpose registers. I can represent 0 through 15 in 4 bits. So this opcode, say, is add. This is the register that contains, and the next 4 bits tell me which register contains the first input number. The next 4 bits tell me which register contains the second number to be added, and the last 4 bits tell me where I'm going to store the result. Okay, if I look at this instruction, it's relatively short. But now what if I had another instruction, still an add, that reads its input from 2 registers but stores its output to something else, like a memory address? Okay. Notice that although these are both adds and they both have 3 operands, this one's longer. Okay. Why is it longer? Because this last operand is a memory address, which requires more bits than in the first case where the last operand represented a register. Okay. In essence, what I'm looking at here is variable length instruction formats. Some instructions, such as the one on the left, are shorter than other instructions on the right. Okay. Now, if I've got variable length instructions, which kind of comes with the territory, I actually wind up using memory a little more efficiently than if they're fixed length. Okay. If I was going to do fixed length here, well, you say, how can this be fixed length? This one's longer than this. Well, there's a very simple way to do fixed length. I figure out which one's the longest, and any ones that are shorter, I either pad a bunch of zeros on the end or I pad a bunch of zeros on the beginning. I probably think of padding them on the end. So I'm not sure how many. I think there's 16 here and there's only 4 here. So think of this instruction on the left with 12 extra zeros stuck onto it. What do I do with the zeros? Absolutely nothing. They're simply stuck on there to make this instruction on the left, quote unquote, the same length as this instruction on the right. Okay. Now, that actually helps me. Okay, that would be an example of making fixed length instructions by padding with zeros. That actually helps me on something I'm going to come to in a minute. Okay. Well, actually, no, let's talk about it now. That helps me simplify the control unit. Why does it help me simplify the control unit? Because the control unit, remember at the very beginning of the instruction cycle, what's the first thing it does? It looks in the instruction pointer, and that's what's in there as a memory address. It goes to the memory, it goes to primary storage, and it grabs the instruction from memory and copies into the instruction register. Okay, but how many bytes does it know to grab? Okay, well, if I'm using variable length instructions, it doesn't, at least not initially. What it really has to do is it has to go grab the first byte, look at the opcode, and then kind of look up that opcode in a table. And what that table says is for this opcode, you've got 3 operands, and they're 4 bits each, so you need to go grab 12 more bits. Okay. Whereas for this opcode, whatever it is, you've got 24 more bits to go grab. Okay. Well, there basically means now the control unit has to make a decision every time it fetches an instruction. It's got to fetch the opcode, it's got to look up the opcode in a table and say how many more bytes does it have to grab, and then it's got to go grab that bytes. That's clearly more complicated than say just going every time I fetch an instruction and grabbing the same number of bits, be it 32 or 64 or 128 or 48 or whatever it is. If I always grab the same number of bits, that's faster. That's simpler. Remember, simpler is faster. Simpler is less complex. Less complex means fewer electrical circuits, means less distance for the electricity to travel, and it's therefore faster. So when we're talking about variable length instructions versus fixed length instructions, there's really 2 issues, or we need to compare them on 2 bases. One is how efficiently do they use storage? Variable length instructions use storage memory more efficiently because they're packing them in there. Okay, whereas fixed length instructions, we've got all those extra zeros to pad the short length instructions out to match the longer ones. Okay, and those zeros are wasted space. Okay, so if you quote unquote took the same program and stored it as fixed length instructions versus variable length instructions, typically storing it as fixed length instructions is going to take somewhere on the order of 40 to 100% more memory to store the same program. Okay. Now, of course, if we're only talking about a few kilobytes of memory, no big deal. If we're talking about gigabytes of memory, now that's a big deal. Okay. So variable length has an advantage with respect to memory. The flip side is this complexity in the control unit associated with the fetch. Okay, and it's not just how many bytes to fetch, but it's also how much to increment the instruction pointer by. Okay. With fixed length instructions, there's no decisions whatsoever. Okay. Whatever the length of the longest instruction is, say it's 8 bytes, I fetch 8 bytes every time. I increment the instruction pointer, excuse me, by 8 bytes. Okay. But with variable length instructions, now I gotta grab the operand, I gotta look it up. How long is it? Grab that many more bytes, and then that's what I implement or increment the instruction pointer by. Okay, so fixed length is a simpler decoding process. Okay, well, the process we just described is what's called decoding. If decoding is simpler, then the fetch should be faster, and that should increase the speed of the overall processor. Although notice I've got a question mark there. We'll come back to that. Okay, so let's talk about clock rate. Kind of avoided this or glossed over this issue this far, but now we got to hit it directly on the money. Okay, so inside the CPU there is a ticking clock. Okay, and that clock generates an electrical pulse every so often. In a modern processor, that pulse is being generated typically a couple of billion times a second. So for example, if we go out and buy a laptop with a 2 gigahertz Core 2 process, Core 2, I don't know, or Core i7 or Core i5 or whatever, that internal clock inside that processor generates a tick, okay, 2 billion times a second. Okay, so what does that mean? Okay, so there's a ticking clock. So what? Well, that ticking clock regulates the fetch and the execute cycles. Okay, and so if this clock is ticking 2 billion times per second, then the assumption is that some fraction of 1/2 billionth of a second is spent doing the fetch, and the remainder of that 1/2 billionth of a second is spent doing the execute. Okay, so here's one way to think of it. Okay, the clock rate for a CPU is the elapsed time needed to fetch and execute the simplest, shortest instruction in the instruction set. And in virtually any instruction set on any CPU, the shortest thing to do is a not. Okay. All right. So, in theory, we'll come back to difference between theory and practice. If this clock is ticking 2 billion times per second, then this CPU can be executing 2 billion instructions per second. Fetching and executing, I should say, 2 billion instructions per second. Okay, if that were the case, then, and if speed mattered, then we would always want the highest clock rate we could get. Okay, so I'd rather have a 3 gigahertz processor rather than a 2 gigahertz processor, because a 3 gigahertz processor in theory would execute 50% more instructions in the same amount of elapsed time, and therefore do 50% more work. Okay, so that means, I don't know, it runs a computation 50% faster, or maybe it means if I'm playing a video game that I can run in HD mode as opposed to some lower resolution or lower number of colors. Okay. So that's the theory behind clock rate. Okay. Now, is it really that simple? No. Okay. Once upon a time it was that simple, but that time is long past. Okay. What mucks it up in the modern world? Okay. Well, in the modern world, several things muck it up, and I've only picked on a few of the more important ones here. Number one thing that mucks it up is memory caches. Okay. Okay. Note the parenthetical here under after fetch with no wait states. Okay. Now we know that. Well, I don't know. I'm not sure if we've covered this yet. Actually, we may not cover this until we get to Chapter 6. But the CPU is one device. Memory is another device. Okay, so there's a chip that sits on the motherboard of your machine. That's the CPU. And then there's these other devices, SIMs or DIMMs, that sit in different slots, and they're the memory. And there's distance between them. And from the point of view of the internals of the CPU, that distance is like hundreds of miles. So if the ALU has to access data from a register, well, that's right next door. Okay, but in comparison, memory might as well be in Los Angeles. Okay. Well, if it's right next door, how long does it take to grab the data and bring it over? Not very long. If, on the other hand, if it's in Los Angeles, how long does it take to grab the data and bring it over? Well, clearly, it takes a while. There's a delay, okay, or what we will later call a wait state, okay. Memory caching is a technique where I take a piece of memory and I actually put it right on the same chip with the CPU, okay, and if I can grab data from that memory cache because it's close, it comes fast, and hopefully with no wait states at all. Whereas if I have to go off the chip and across the motherboard and over to the memory circuitry, now there's going to be a delay. Okay, so best case 2 gigahertz processor, 2 billion instructions per second. But if the fetch takes longer than 1/2 billionth of a second because I'm grabbing data from quote-unquote far away, then in the interim, while I'm waiting for the data to get there, what's the CPU doing? Picture the CPU as, somebody sitting in a chair, leaning back, twiddling its thumbs, watching the hourglass on a web page, waiting for the page to refresh. Okay. So, that's, picture you're doing your research. Do you want a fast, for a term paper, do you want a fast internet connection or do you want a slow one? How much are you going to get done in an hour? Well, if you've got a fast internet connection and every click, instantaneously brings up a new page, you're clearly going to get more done than if every time you click the thing, you got to sit there and twiddle your thumbs for 5 to 15 seconds waiting for the page to show up. Well, that's what we're talking about when we're talking about memory caching, and we will come back to that in Chapter 6. Okay. So in theory, 2 gigahertz, 2 billion per second. In reality, probably not, because there's an awful lot of these wait states. Okay. Second thing that complicates matters, multiple core processors. Okay. An Intel Core i7, for example, that would be a modern processor used in a laptop or a desktop, is typically a dual core processor. What does that mean? It means it's got 2 CPUs embedded in it. Okay. Both of those are running on the same clock. Okay. So if that clock is 2 gigahertz, each of those cores is a distinct CPU. In theory, each of those cores can execute a separate instruction. So 2 gigahertz in the case of a dual-core processor, in simplistic theory, means 4 billion instructions per second, not 2. Okay. Multiple ALUs per core. Well, if I can duplicate CPUs, maybe I can go down inside the CPU and find some things to duplicate that will speed things up. Well, what does all the arithmetic and logic work? The ALU. What if I had multiple ALUs inside a single CPU? If I had multiple ALUs and if I could keep them all busy, then each individual CPU could, in theory, be executing multiple instructions, 1 per ALU, per clock cycle. Okay, so for example, let's say I've got a single CPU, but it's got 4 ALUs, and there's a 2 gigahertz clock rate. Okay, so 2 billion instructions per second times 4 ALUs is 8 billion instructions per second. Last technique, which I'm just going to mention but not talk about because it's a little more complicated, and we'll get to it in Chapter 6, is something called pipelining. Think Henry Ford assembly line. Okay, add all this up, and you can get substantially higher rates of instruction execution than would be implied by the clock rate, assuming the memory caching is working. Leave some of this stuff out, and not only don't you get the clock rate as the number of instructions executed per second, you probably get considerably less, mostly due to this issue of wait states, but also due to the fact that many of the instructions you are executing are not the simplest instruction. Okay. All right. Now on to registers. We have 2 basic types of registers in any CPU. We've got what are called general purpose registers, and then we have special purpose registers. Okay. General purpose registers are what the ALU uses to hold inputs and outputs. Okay. So when the ALU adds 2 numbers together, each of those 2 numbers before the add takes place has to be sitting inside each has to be inside a general purpose register. So 2 general purpose registers for the 2 inputs. Literally what happens when the ALU quote unquote doesn't add, for example, is the electrical signal, it generates electrical signals passed on or based on the contents of those general purpose registers, feeds them through circuitry in the ALU, which performs the add, generating electrical signals which represent the result, which then go to an output general purpose register where those electrical signals are quote unquote captured and stored. Okay. Now, why do I care about that? Well, it goes back to this issue of speed. Okay, the ALU can be fast because it's always reading from these general purpose registers. Okay, if I've got a fairly simple computation involving only one or two steps, then a relatively small number of these general purpose registers is probably enough to support that computation. But think to one of your finance classes and imagine the most ugly, complicated formula that they went over in there for computing, I don't know, continuous interest or monthly payments or what have you. So you probably had one of these formulas that was, 1 minus n raised to the number of periods times this, that stuck in parentheses over something else, take the square root of the whole mess, and then that whole thing was multiplied by something else. Okay, clearly that's a long sequence of complicated operations, and if you were to sit there and do them one at a time, you would generate a lot of intermediate results. So I do this and store the result. Then I would use that result as an input to another step, which would generate another intermediate result, and I'd store that, and so on and so forth. The more complicated the computation, the more of those intermediate results you generate, and the more general purpose registers you need to support the computation. Okay. So, what happens if you don't have enough of them? Well, if you don't have enough of them, now what you got to do is you got to start swapping these intermediate results between general purpose registers and memory. And remember, memory is far away and therefore slow to access. So if the ALU is constantly having to bounce intermediate results back and forth between general purpose registers and memory because it doesn't have enough general purpose registers, that's going to slow everything down. We're back to wait states again. Okay. So up to a point with respect to general purpose registers, more is better. Okay. But what happens eventually is you hit another economic reality, the law of diminishing returns. Okay. So, going from, say, 2 to 4, definite improvement. Going from 4 to 8, definite improvement. Going from 8 to 16, probable improvement. Going from 16 to, 1,000, not sure that's going to buy you a whole lot. Why? Because the question is, how often does your ALU have to do computations that are so complex that you would need 1,000 intermediate processing results? Okay. If that's something your processor does all the time, then maybe you need 1,000 general purpose registers. But if you look at typical programs running on typical computers, what you find is a dozen, 2 dozen, 3 dozen general purpose processors per ALU is probably enough. Now, of course, if you've got multiple ALUs, then you want that number per ALU, so maybe that pushes your general purpose register count up to several dozen. Okay. But the bottom line is a few dozen per ALU is enough. Okay. Stepping back briefly here to the Intel manual, if we come to the basic execution environment, and let's see if I can find where that is. Actually, no, I think it's under the architecture. No. Let me pause a second while. Okay. No, basic program execution registers. Okay. So you'll see. Here in the Intel manual, okay, they talk about general purpose registers, and they say there are 8 registers available for storing operands and pointers. Okay, that doesn't quite sound like a couple dozen for ALU, but the fact is there's some others here that they use that they're not talking about right at this point. There's also something called segment registers, which are unique to Intel, and I don't want to talk about those. Okay. And then they go into detail and talk about what the general purpose registers are and note what they tell you they're for. Operands for logical and arithmetic operations, operands for address calculations, and memory pointers. That's basically what you use general purpose registers for. Okay. What about these special purpose registers? Okay. Well, we've already talked about a few of them. The instruction pointer is a special purpose register. Okay, that's where we store the instruction immediately. It's after it's fetched and before we start breaking it up into pieces and storing those pieces. There's also one that's sometimes called, I'm sorry, that's this one, the instruction register. There's also the instruction pointer, sometimes called the program counter, that contains the memory address of the next instruction we're going to fetch. So remember, when we first start the fetch cycle, we look at that instruction pointer. It tells us where in memory we want to fetch. We go grab either a fixed or variable number of bytes from that location, and then we increment that instruction pointer immediately to point to the beginning of the next instruction. And once we've finished the rest of the fetch cycle and gone through the execute cycle, go back to the beginning of the next fetch cycle. That's the one we're going to grab. Okay, and it's that incrementing of the instruction pointer each time that gives us the default sequential flow through a set of instructions or a program. Okay, now the one you haven't seen yet, this goes by a lot of different names. Okay, this name I tend to use is actually a throwback to IBM mainframe days, Program Status Word. That's what IBM called it. Okay, actually Intel calls it the E-flags register. Okay. And let's look at the description. The E-flags register report, which should say reports, on the status of the program being executed and allows limited control of the processor. Okay. And then here's the EIP, contains a 30-bit pointer to the next instruction to be executed. So this EIP is the instruction pointer. Okay. So, what could be in this program status word? Well, first off, think of it as a set of bits, and think of each bit as representing a different thing, or think of very small groups of bits as representing different things. Okay, what can be in there? Okay, well, one thing that tends to get stored in there is the result of comparison operations, and typically 2 bits in the PSW are allocated for that. So basically, less than, equal to, or greater than. There's 3 possibilities, so that's 2 bits it requires. And so you got 4 values that can be stored in 2 bits, and you've got 3 different comparison results that could be in there, so one of them's unused. What happens if the processor generates an error? So for example, what happens if you try to divide by 0? Well, that generates an internal hardware error, and there's a bit in the program status word that's set to 1 every time that happens. And at the end of every execute cycle, there's a hardware check on this PSW, and if that particular bit or any of the other bits that would contain error codes is set to 1, then you don't go grab the next instruction of the program. There's an immediate something else. Okay, and we'll talk about that something else when we get to operating systems. So any sort of processing error, divide by 0, overflows, underflows, can all generate conditions which are represented by setting one or more specific bits of this program status word to true, or turning them on. Okay, so that's the basic purpose of this. When they say register support on the status of the program being executed, that's what they're talking about. Has it generated any errors? If so, what is the specific error? Okay, so that's what the PSW is used for. It's not something that programmers tend to use directly, but it's a very important special purpose register.